Hello everyone, my name is Katie Giunta and I'm a sophomore this year. For Undergrad Research Month, I will be presenting on the work I did this past summer with Professor Bob Pike on pyridine interactions with surface copper iodide. Since everything had to be online because of the pandemic, instead of working in the lab, I learned how to use a computational software called Gaussian to examine the bonds in the molecules we were looking at. The Gaussian program only runs on the school's high-performance computers, so I had to access it through my personal laptop using the secure shell client. Once I could log into the HPC, I was able to run commands through Gaussian and then use the William & Mary virtual desktop to view the final computations. It took quite a while to get through all the kinks and get a final product because usually this is done on the school computers. However, with a lot of Zoom calls, I was finally able to get my first computations done. The molecule I ran through successfully was copper 4, iodine 4, pyridine 4, and the blue box shows its structure. Once I had created the structure on my laptop, I ran it through the Gaussian program with the kind of calculations I needed specified, and the text on the right shows the completed calculations. Every atom in the molecule had a spot on the far left column and then an XYZ position given to it. There's obviously a lot more output from the calculations, but this was the part that's easiest to visualize in a PowerPoint. One of the fun parts of completing a calculation is that there's a random quote at the bottom of the text so that you know it has been done successfully. For example, I took a screenshot of the quote from when I first did my calculations on water, and it says, "In the woods we return to reason and faith." This ensures that you know that your calculations have been completed successfully. The completed data is then compared with the observed interactions with the compound we were examining. While I was working remotely, Professor Pike and an undergrad student were working in the lab looking at the larger compound interactions. The molecule that I did calculations on was a lot more simple than the final one, but a good way to get a feel for what the group was doing and the calculations we would ultimately run through Gaussian. The more complicated computations were handled by the other members of the team, and they were looking at how pyridine molecules interact with the surface of copper iodine solids, especially when there are some defects in the surface. They used Gaussian to look at density functional theory and molecular dynamics calculations. Density functional theory, or DFT, looks at the electronic/nuclear structure of ground state systems and can provide insight on the properties of these compounds. Molecular dynamics calculations serve to calculate motion and equilibrium of each atom or molecule we look at. Our calculations found that pyridine has areas of reactivity and a strong donor region at the nitrogen atom. This region is drawn to the defects in the copper iodine surface, and the pyridine molecules cluster around and fill in the defect site. That's what's circled in red on the pictures on the bottom. The pyridines line up vertically with the nitrogen facing down, interacting with the copper iodide. The DFT calculations revealed that the pyridine molecules are really tightly bound to one another when they're in the defect due to increased hydrogen bonding between the molecules. The summer ended, and the other members of the team kept working with the copper iodine surface pyridine questions, but I transitioned to working in person with Professor Pike in his lab. While we were working, I ran some calculations on acetonitrile, which is the molecule shown here, but this research didn't end up going very far. However, it was very cool to apply my knowledge from last summer to this new work that we were doing. This brings me to this coming summer, where hopefully I'll be working with Professor Pike again and continue the research we are doing right now on the creation of bismuth double salts. My project will focus mainly on two things, the first being the creation of the bismuth double salts, and the second is looking at the properties that these salts have. Bismuth double salts have two different parts in addition to the heavy bismuth metal. For us, this is an iodine and either another metal, a big organic group, or basically anything we can get to synthesize with the bismuth. This is done mainly through crystallization techniques, where we combine the reagents with a liquid that they are both soluble in, and then let it sit, and hopefully it will form crystals of our new product. From here, we put the sample into the X-ray crystallography machine and hope that it confirms that we have successfully made a bismuth double salt. This research is important because double bismuth salts have never actually been synthesized before, and I will be using all the chemistry knowledge I've gained to accomplish this with Professor Pike. Towards the end, there will certainly be a computational part of this once we've created our product, and I look forward to applying the knowledge I gained last summer to my future projects.